Hi class, we are now on 4.4. It's going to be broken up into two different sections. So we're on 4.4a, describing electron configuration. Now, if the last section didn't make sense, I hope that this will clarify some of that information. So the quantum model predicts electrons occupy energy levels, which we number 1, 2, 3, etc., and sublevels labeled S, P, D, and F. We are now going to look at electron configurations of a series of atoms, so this will hopefully make more sense. This shows the atomic number located on the periodic table. So remember that this tells us that the number of electrons that we're going to be looking at matches the atomic number. So we're going to be dealing at this point with neutral atoms. So when we talk about electrons, that means that the number of electrons we're dealing with, that atom also has that same number of protons. So that's where we can always get the atomic number from. And we're dealing with neutral atoms. So this diagram shows the relative energy difference between the different energy levels and their sublevels. The general rule, electrons occupy the lowest available energy levels. This is called the ground state. So remember I told you there's a bookcase and we start adding books at the bottom up. So that's what we're going to do here. We start at 1 and we go up. So let's start with hydrogen. So if you notice, this diagram is very similar to what we're using here. It's just more lined up where this one's kind of spread out so you can see it. But if you move everything over and shove it over, that's what you're seeing here. Okay, so hydrogen has an atomic number of 1, which means, excuse me, it has 1 electron. This 1 electron occupies the lowest energy level and sublevel possible. So this is a 1s. This is represented on the energy diagram by drawing a single-headed arrow in 1s, and we tend to always write the first one as up. We also have an electron configuration. So we have a diagram and we have an electron configuration where you don't use the diagram, you just write it out. And so we match it to what we show here. So we write a 1 and an S and a superscript. Has to be a superscript. If you write it next to parallel, it's wrong. 1S1. I know we're online, but you're going to go on in chemistry and you will be in person in lab for 24A. And any of these things will be marked wrong because there's certain rules and certain etiquette that may not make sense to you, but this is how everything stays consistent. And usually when somebody gets something wrong, then they will always follow the rules the way they need to, even if it's just a mistake in the beginning. So superscript 1. This means, so this is said as 1s1. That's how you would say this. The electron configuration of hydrogen is that supposed to say is? The electron configuration of hydrogen as, okay, 1s1. This means 1s, that the energy level is 1, the sublevel is s, and there is 1 electron that is in this orbital. Let's look at helium. Helium has an atomic number 2, which means we're dealing with 2 electrons. So we fill them in the lowest level. Nothing changes. So they're both now in the 1s level. And on the diagram, we represent 2 electrons, one in the up direction, one in the down direction. This signifies the spin because they have magnetic fields, and they have to be oriented in opposite directions in order for them to be next to each other. Similar to magnets, if you put them in the same, they call them poles. If they have the same poles, they will repel each other. So make sure you draw one up and one down. If you draw them both up, that's wrong. If you draw them both down, that's wrong. They have to be one up and one down. Why? Because chemistry is all about stability and lowest energy. And the most stable is with 1 arrow up and 1 arrow down. If you draw them together, up or down, they are not stable. They're very unstable, like that. Okay, so the electron configuration for helium is 1s2. Both in the 1s energy level and sublevel, and 2 electrons are contained in that. Lithium. Lithium has atomic number 3, which means it has 3 electrons for a neutral atom. The first 2 electrons fill the first energy level, and then we have 1 more electron, and it goes into the 2s energy level. So we write them. So again, we write the arrow up, and the electron configuration for lithium is 1s2, 2s1. And that these superscripts, if you add these together, there's a total of 3, which matches the 3 here. Beryllium is 4. So again, we fill up the 2s. We can only add 2 electrons for each orbital. So once we hit 2, we have to go into the next one. So here we have 2 on the 1s level and 2 on the 2s level. And this is written as, oh, did I not mix it? Sorry, here we go. Is 1s2, 2s2, 2 plus 2 equals 4, which is the 4 electrons we have here, which matches the atomic number for a neutral atom. Boron is 5. Now, we're just going to keep doing the same thing. It has 5 electrons. We add 2 to the 1s2, 2 to the 2s2, and then we have 3 orbitals empty. We tend to write the first arrow in the first one. It doesn't really matter, but it's more of just a way that we do it. So we write it up, and we write in the first one. So this is 1s2, 2s2, 2p1, and you add those together, that's 5 electrons. Okay, now we get to something different. We are on carbon, and carbon has an atomic number of 6, so we add 2 to the 1s2, 2 to the 2s2, and now we have 2 electrons. So do we pair them? No, we do not. Chemistry is all about lowest stable energy. If we pair these two, that is not stable energy. We have 3 orbitals to put them in, so we can separate them right now. That's Hund's rule. If empty orbitals of the same energy are available, electrons singly occupy orbitals instead of pairing them together until you're forced to pair them together, which means that when we go on to whatever, I think nitrogen 7, we would add 1 more arrow in the 2p, that's 3. We get to oxygen, we would have to force another electron into one of these orbitals, and it would be facing down. So that's the other thing. All the arrows are facing the same direction as well until we have to pair them together. So in this one, the electron configuration is 1s2, 2s2, 2p2. And if you have a problem remembering this, just remember it like students in a dorm. Let's say that you have to give out the rooms. So what you'll do is you'll give out rooms to one student. So each student has their own room until you can't do that anymore, and then you have to have people bunk together. That's the same thing. We add them into empty orbitals until we cannot. So here are the electron configurations for the remainder of the row 2 elements. And I put a box here so you can see. If you add up the superscripts, it tells you what they are. 2, 2, 5, that's 1, that's 5. 2, 4, 6, that's atomic number 6. 2, 4, and then 3, that's 7. 2, 4, and 8, 2, 2, and 4 is 8. And you can see that these superscripts match the atomic numbers because they match the electrons, which are neutral elements. So in this case, there is, so we move across the periodic table in row 2. Row 2 is the second energy level. This means that here the electron is, I'm trying to figure out how to say this. Neon, the last element in row 2, has completely filled energy levels. That means that when we look on here, up into 2p6, all of these are filled up. Everything's filled up for as much as they can. Now, I had said in one of the other sections that it has to, the row equals the energy level. So all of these are in row 2, so they all end in row 2. That's the highest energy level. That's how you know if you are on the right track. Look on the periodic table, see what row it's in, and if it's not in the, well, there is some exceptions to this, so I'm only saying this right now. There's some things that are going to change. Remember that 3D and so forth, but we won't worry about that at the moment. Locate the element or atom on the periodic table. Look at the row. When you do electron configuration, it should end with that same row number. So if it's a row 2, it should end in row 2, and it does. So that's what I'm trying to point out. If you're in row 3, it should end in row 3. Okay, so let's do some examples. What is the electron configuration for silicon? So let's make sure you guys understand the terminology here, because the terminology is where some of the problems are. Electron configuration is this. This is a diagram or orbital diagram. So you need to know what's being asked of you. This is a condensed version of the periodic table. We jump and skip the transition metals. So this is asking for silicon. So if we're in row 3, remember what I told you? Then this means that my last highest energy levels should end with a 3 in it. That's a good way of doing housekeeping and checking that you are following and on the right track. So row 3, we'll cheat and say, yeah, it's in row 3. Okay, so here's another thing I want to point out, and it's not really, they haven't really discussed it yet. See this group 1? This is all s orbitals. Everything here ends in an s. This ends in 1s, this ends in 2s, this ends in 3s. This ends in 2s2, 2s3, 3s2. If that doesn't make sense, it will. These are all p orbitals. This is p1, p2, p3, p4, p5, p6. So when you fill them all, that's where you get to this point. That may not make necessarily sense right now, but do you see that this is a p orbital, p1, this is p2. That's the p2. If I have phosphorus, it's going to be a p3. If I have sulfur, it's going to be a p4. Chlorine is going to be a p5, and argon is going to be a p6. That will help you understand if that makes sense. If it doesn't, don't worry about it. Just keep following the numbers. So let's see how we do. Here's your diagram, and if you're having problems in the beginning, I would strongly suggest making a blank one of these so that you can start seeing how this needs to be, and then you can transfer it to writing it like this. So we have silicon of 14. So 14, there's 2, 4, 6, 8, 10, 12, and then we have empty orbitals, so we separate them, and we have 2. So now we can write it 1s2, 2s2, 2p6, 3s2, and 3p2. This is the electron configuration. It represents 14 electrons total for a neutral silicon atom. And that's exactly how you would handle anything that's being asked for electron configuration. If you need an orbital diagram, make sure you get comfortable with using an orbital diagram. I've put several up, copy them down, and then you can use that until you're full, then you can transfer to electron configuration. So here is the diagram. It's this is just a generic blank one, but could help you understand. This is kind of a guide in order to move to electron configuration, because we don't always stay working on orbitals, but we do keep with electron configuration throughout chemistry, because we're going to start dealing with ions, and that's when we take electrons away and we add them. So you got to make sure that you're very comfortable with them during the neutral state. Okay, so let's take a look at doing some problems. Again, this is just a blank thing that gives you an idea of what this looks like with the different shapes and orbitals, the probability. So write the electron configuration for carbon. So the orbital diagram's already been done for you. You just have to transfer that information over. So we see the 1s is filled, the 2s is filled, and we have 2 electrons and 2p. So we transfer that over and write that out, and that is the correct electron configuration for carbon. And if we didn't know this with carbon, we were just given this, all we have to do is add these together, and that gives us our atomic number, and we could look this up on the periodic table. Write the electron configuration for neon. So neon is 10. We don't even need the orbital diagram, but if you are new to this and you're not comfortable, then you would want to fill this up. And this is what I mean by filled orbitals. Neon is that anything that's in the noble gases at the end of the periodic table, they fill up whatever row this is. So I think argon's underneath it, so this would be a 3p, so it would be moved up. But they all fill the p orbitals up. So in this case, we write it out. We have 1s2, 2s2, and 2p6. Add those up, that's 10. We have a filled electron configuration